This is a walkthrough of the solutions for the COS217 midterm from spring 2020, problem 4. In 4a, we're given a program that attempts to concatenate strings from standard input to build a long string, so long as there is input. We're told that there's a bug in the program and that it occurs only under one very specific condition. We're asked to find the bug. Let's look through the program and see if we can find some potentially problematic pieces and reason about whether or not this will in fact be a bug. We'll start in main. The very first thing we see is a local variable buffer that's given a limit of 100 bytes. This should jump out at us and say, oh no, we're going to read into that buffer and we could overflow the buffer. However, the problem assures us that that will not be an issue. Each read from standard in will fit in buff. So let's continue on. We start out with the length of the string as 0 and the capacity of the string is 0. And so we create a new string of length 1 that's long enough to hold the empty string. The +1 will give us the null byte at the end of the empty string. And we point a local car pointer string at that allocation. This will be our concatenated string. Now we're going to use scanf to read in a string at a time. And we're going to check that scanf returns 1. Scanf returns the number of its format specifiers that were able to be read in. So 1 is the success case here. And if it reads in EOF, it will have failed to read. It will not return 1. It will return 0 and will break out of the while loop. So for each string that it reads in, we find the length of that string and add it to the length of our string thus far, creating the length of the new string. If that length is greater than the capacity that we've allocated, we need to allocate more space. So we're going to increment our capacity by some constant factor k, and then we're going to reallocate asking for that new capacity. One could imagine a concern if k is too large to fit in a long. However, k here is a constant, it's always 500, and I can assure you that 500 can be represented in a long without overflowing into negatives. One might also be concerned that if we continue incrementing by k enough times, we might eventually get a capacity that would overflow a size t. However, the problem again tells us that size t will always be sufficient to store the capacity of stir. So we reallocate stir to be capacity +1, again the +1 for the null byte, so we haven't made that common error. And once we've done so, we cat buff onto the end of stir. We continue doing this until we no longer read a string, at which point we print out the length and our string. We don't make a memory management mistake by forgetting to free string and thus create garbage, memory leak, and so we have what appears to be a correct program. But thinking about those common memory management errors, we've forgotten one common one. Recall that realloc, if you attempt to reallocate less space, we'll keep the allocation as is. So if we have stir on the stack, pointing into the heap at some allocation, if we were to ask for less space, stir wouldn't change. If we're to ask for more space, we're going to look here at the end of the current allocation, and if it's available, we will allocate in place. However, if we were to do that again, in a location where we don't have space at the end to fulfill our new allocation, what realloc will do, it will go and find somewhere else in the heap something that is big enough, transfer all of the data from the old allocation into the new allocation, leave the extra part as uninitialized, free the old allocation, and return a pointer to the new allocation. This is the case where we suddenly see the problem. When realloc changes stir in place, everything is fine. However, if realloc returns a pointer to the new allocation, we never catch it. This means that several bad things happen. Number one, that new allocation is a memory leak because we have no way to access it. Number two, stir has been freed, but we're still pointing at it. That makes stir a dangling pointer. And in fact, we continue accessing it in that line 19 where we stir cat onto it. So stir is now going to be accessing a dangling pointer. And then down on line 23, when we are good programmers and free our allocation, we're going to free something that's already been freed, and that's a double free. So our fix, we can catch the return value from realloc and assign it back into stir. A reasonable question might be, but what happens if it returns null? But thanks to the problem, allocation never returns null, so this is totally safe to do under this circumstance. In part B of problem 4, the student was asked to expand their str.h interface implementations from assignment 2. String.h, the standard library, contains another function, stirdupe, that copies a source string into a new string that was allocated in that method and returns the new string. This problem asks the students to write strduplicate as the str.h analog of string.h's stirdupe. It also asks to follow all of the proper programming style, including writing a comment. So let's start out with the comment. Once we have that, we can make the implementation accord to this contract that the comment lays out. So, the comment, we can start off saying, the behavior of the method, it copies its parameter into a newly allocated string, and we use the parameter name in this description. Now we have to take into account what will it return. If we're able to create the new string and copy it over, we should return it. If not, we will return null. The last thing we should note is because we have allocated memory that stirdup will never free, the string module will never free, we have to let the client know, the caller know, as part of the contract that it is now responsible for that memory. Now with all of this set, we're ready to implement the function. So let's start out with our signature. The first thing that we want to do is we want to validate that our parameter is not null. This follows our programming style from assignment 2. Now we need to have a local variable that will serve as the pointer to the new string. We're going to allocate space for that new string. And the amount of space we need is the length of the source string plus 1 for the null byte. As always, we have to check our mallocs. And we will accord to what our contract said, which was that if we could not malloc, we would return null. Now we have to do the copy. We could, in fact, traverse using our idiom of iterating through the string until we reach the null byte. But in fact, we already have a method from our library that does a copy for us, so we might as well use it. Stir copy copies into the dest from the source, and it returns the destination string, so that means that we can just return its return value. And that completes our stir duplicate analog of stirdup. We check our parameter, we allocate enough space, we check our allocation, we do the copy, and we return the new string.